In mathematics, and more specifically in algebra, a ring is an algebraic structure with operations that generalize the arithmetic operations of addition and multiplication. Through this generalization, theorems from arithmetic are extended to non-numerical objects like polynomials, series, matrices and functions. Rings were first formalized as a common generalization of Dedekind domains that occur in number theory, and of polynomial rings, and rings of invariants that occur in algebraic geometry and invariant theory. They are also used in other branches of mathematics such as geometry and mathematical analysis. The formal definition of rings dates from the 1920s. Briefly, a ring is an abelian group with a second binary operation that is associative, is distributive over the abelian group operation and has an identity element. The abelian group operation is called addition, and the second binary operation is called multiplication by extension from the integers. A familiar example of a ring is the integers. The integers form a commutative ring, since the order in which a pair of elements are multiplied does not change the result. The set of polynomials also forms a commutative ring with the usual operations of addition and multiplication of functions. An example of a ring that is not commutative is the ring of n times n real square matrices with n2. Finally, a field is a commutative ring in which one can divide by any non-zero element. An example is the field of real numbers. Whether a ring is commutative or not has profound implication on its behavior as an abstract object, and the study of such rings is a topic in ring theory. The development of the commutative ring theory, commonly known as commutative algebra, has been greatly influenced by problems and ideas occurring naturally in algebraic number theory and algebraic geometry. Important commutative rings include fields, polynomial rings, the coordinate ring of an affine algebraic variety, and the ring of integers of a number field. On the other hand, the non-commutative theory takes examples from representation theory, functional analysis and the theory of differential operators, and the topology. Definition and illustration. The most familiar example of a ring is the set of all integers, z, consisting of the numbers -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. The familiar properties for addition and multiplication of integers serve as a model for the axioms for rings. Definition: a ring is a set R equipped with binary operations plus and satisfying the following three sets of axioms, called the ring axioms. 1. R is an abelian group under addition, meaning that plus C equals a plus for all A, B, C in R. A plus B equals B plus A for all A, B in R. There is an element 0 in R such that a plus 0 equals A for all R in R. For each R in R there exists minus R in R such that a plus equals 0. 2. R is a monoid under multiplication, meaning that C equals A for all A, B, C in R. There is an element 1 in R such that a 1 equals R and 1 R equals A for all R in R. 3. Multiplication is distributive with respect to addition. R equals plus for all A, B, C in R. R equals plus for all A, B, C in R. Notes on the definition as explained in history below. Many authors follow an alternative convention in which a ring is not defined to have a multiplicative identity. This article adopts the convention that, unless otherwise stated, a ring is assumed to have such an identity. A structure satisfying all the axioms except possibly the existence of a multiplicative identity 1 is called a Rng. For example, the set of even integers with the usual plus and is a Rng, but not a ring. The operations plus and are called addition and multiplication, respectively. The multiplication symbol is often omitted, so the juxtaposition of ring elements is interpreted as multiplication. For example, xy means xy. Although ring addition is commutative, ring multiplication is not required to be commutative. Add need not necessarily equal bar. Rings that also satisfy commutativity for multiplication are called commutative rings. Books on commutative algebra or algebraic geometry often adopt the convention that ring means commutative ring to simplify terminology. The additive group of a ring is the ring equipped just with the structure of addition. Although the definition assumes that the additive group is abelian, this can be inferred from the other ring axioms. Basic properties. Some basic properties of a ring follow immediately from the axioms. The additive identity, the additive inverse of each element, and the multiplicative identity are unique. For any element x in a ring R, one has x0 equals 0 equals 0 x and x equals x. If 0 equals 1 in a ring R, then R has only one element, and is called the zero ring. The binomial formula holds for any commuting pair of elements. Example: integers modulo 4 equip the set with the following operations. The sum in Z4 is the remainder when the integer x plus y is divided by 4. For example, and the product in Z4 is the remainder when the integer xy is divided by 4. For example, and then Z4 is a ring. Each axiom follows from the corresponding axiom for Z. If x is an integer, the remainder of x when divided by 4 is an element of Z4, and this element is often denoted by x mod 4, or, which is consistent with the notation for 0, 1, 2, 3. The additive inverse of any in Z4 is, for example, 2 by 2 matrices. The set of 2 by 2 matrices with real number entries is written with the operations of matrix addition and matrix multiplication. This set satisfies the above ring axioms. The element is the multiplicative identity of the ring. If and then while, this example shows that the ring is non-commutative. More generally, for any ring R, commutative or not, and any non-negative integer n, one may form the ring of n by n matrices with entries in R. See matrix ring. History. Dedekind. The study of rings originated from the theory of polynomial rings and the theory of algebraic integers. In 1871, Richard Dedekind defined the concept of the ring of integers of a number field. In this context, he introduced the terms ideal and module and studied their properties. But Dedekind did not use the term ring and did not define the concept of a ring in a general setting. Hilbert. The term Zahlring was coined by David Hilbert in 1892 and published in 1897. In 19th-century German, the word ring could mean association, which is still used today in English in a limited sense. So if that were the etymology, then it would be similar to the way group entered mathematics by being a non-technical word for collection of related things. According to Harvey Cohn, Hilbert used the term for a ring that had the property of circling directly back to an element of itself. Specifically, in a ring of algebraic integers, all high powers of an algebraic integer can be written as an integral combination of a fixed set of lower powers, and thus the powers cycle back. For instance, if a3 minus 4a plus 1 equals 0, then a3 equals 4a minus 1, a4 equals 4a2 minus a, a5 equals minus a2 plus 16a minus 4, a6 equals 16a2 minus 8a plus 1, a7 equals minus 8a2 plus 65a minus 16, and so on. In general, n is going to be an integral linear combination of 1, a, and a2. Frankel and Noether. The first axiomatic definition of a ring was given by Adolf Frankel in 1914, but his axioms were stricter than those in the modern definition. For instance, he required every non-zero divisor to have a multiplicative inverse. In 1921, Noether gave the modern axiomatic definition of ring and developed the foundations of commutative ring theory in her monumental paper, Ideal Theory in Ring Bereichen. Multiplicative identity. Mandatory versus Optional Frankel required a ring to have a multiplicative identity 1, whereas Noether did not. Most or all books on algebra up to around 1960 followed Noether's convention of not requiring a 1. Starting in the 1960s, it became increasingly common to see books including the existence of 1 in the definition of ring, especially in advanced books by notable authors such as Utton, Uttier, MacDonald, Bourbaki, Eisenbud, and Lang. But even today, there remain many books that do not require a 1. Faced with this terminological ambiguity, some authors have tried to impose their views, while others have tried to adopt more precise terms. In the first category, we find for instance Gardner and Wiegand, who argue that if 1 requires all rings to have a 1, then some consequences include the lack of existence of infinite direct sums of rings, and the fact that proper direct sums of rings are not subrings. They conclude that, in many, maybe most, branches of ring theory the requirement of the existence of a unity element is not sensible, and therefore unacceptable. In the second category, we find authors who use the following terms: rings with multiplicative identity, unital ring, unitary ring, ring with unity, ring with identity, or ring with 1. Rings not requiring multiplicative identity, RNG or pseudo-ring. Basic examples: commutative rings. The prototype example is the ring of integers with the two operations of addition and multiplication. The rational, real and complex numbers are commutative rings of a type called fields. An algebra over a ring is itself a ring. These are also modules. Some examples: any algebra over a field. The polynomial ring Rx of polynomials over a ring R is itself a ring. A free module over R of infinite dimension. The integers with an irrational number C are joined. A free module of infinite dimension if C is a transcendental number. A free module of finite dimension if C is an algebraic integer. The set of fractions whose denominators are a power of n, a non-free module. The set of decimal fractions, where d is a square free integer of the form 4n plus 1, a free module of rank 2, cf. quadratic integers, the Gaussian integers, the Eisenstein integers. Also the generalization, a comma ring. The set of all algebraic integers forms a ring. This follows, for example, from the fact that it is the integral closure of the ring of rational integers in the field of complex numbers. The rings in the previous example are subrings of this ring. The set of formal power series R, x1, xn, over a commutative ring R is a ring. If S is a set, then the power set of S becomes a ring if we define addition to be the symmetric difference of sets and multiplication to be intersection. This corresponds to a ring of sets and is an example of a Boolean ring. The set of all continuous real-valued functions defined on the real line forms a commutative ring. The operations are pointwise addition and multiplication of functions. Let X be a set in R a ring. Then the set of all functions from X to R forms a ring, which is commutative if R is commutative. The ring of continuous functions in the previous example is a subring of this ring if X is the real line and R is the field of real numbers. Non-commutative rings. For any ring R and any natural number n, the set of all square n by n matrices with entries from R forms a ring with matrix addition and matrix multiplication as operations. For n equals 1, this matrix ring is isomorphic to R itself. For n greater than 1, this matrix ring is non-commutative. If G is an abelian group, then the endomorphisms of G form a ring. The endomorphism ring end of G. The operations in this ring are addition and composition of endomorphisms. More generally, if B is a left module over a ring R, then the set of all R linear maps forms a ring, also called the endomorphism ring and denoted by ENDR. If G is a group and R is a ring, the group ring of G over R is a free module over R having G as basis. Multiplication is defined by the rules that the elements of G commute with the elements of R and multiply together as they do in the group G. Many rings that appear in analysis are non-commutative. For example, most Banach algebras are non-commutative. Non-rings. The set of natural numbers n with the usual operations is not a ring, since it is not even a group. For instance, there is no natural number which can be added to 3 to get 0 as a result. There is a natural way to make it a ring by adding negative numbers to the set, thus obtaining the ring of integers. The natural numbers form an algebraic structure known as a semi-ring. Let R be the set of all continuous functions on the real line that vanish outside a bounded interval depending on the function, with addition as usual but with multiplication defined as convolution. Then R is a Rng, but not a ring. The Dirac delta function has the property of a multiplicative identity, but it is not a function and hence is not an element of R.